Hey guys, in the past couple of lectures, we rather deviated from our original approach and our discussions have largely been mathematical. In one of these sessions, we talked about differentiating linear, homogeneous, ordinary differential equations from that of linear, non-homogeneous and non-linear. This was purely mathematical. And in a subsequent session, we discussed about translating a given ODE into a form that can directly be fed into softwares like MATLAB so that we are able to ascertain the solution easily. So this was, or these sessions were rather a bit of a digression from what our original intent was, but they were necessary because understanding the different forms of ODE will lend us the right approach to solve them. And also we definitely need the support of our computing machines, so therefore it is also rather vital to express a given equation in a way that could be easily understood by machines. So even though they were some sort of a distraction or a digressions, they were critical ones. So having gone through those distractions, now let us get back to our original path and let us begin by having or setting up problems that have physical relevance. Now, all these discussions started off with an example or with an instance wherein we found a bike with a bent rim. So what we essentially observed was the atoms that constitute this rim have been relocated and or dislocated, and we said that the force that caused the dislocations of these atoms, it depends on the positions of the atoms, so that rendered us an ODE, and from that we were able to solve for the position of the atom at a given time t. So what it essentially means is when you have a crystalline system, you impose a force onto the system and the force experienced by individual atoms depends on its position. Then we would be able to come up with an equation or a solution wherein we will be able to say at a given time t what will be the position of the atoms in response to this force. Now let us deviate from this instance to an even more or equally relevant example. So let us instead of considering a bike that has already been deformed, let us for once be the perpetrator of that particular action. Let us rather try to kick this particular bike or impose a force on the bike. But one key difference being, now this time your friend is rather sitting on the bike. Maybe you want to have some fun, I don't know, for one reason or the other you want to impose or you want to kick the rim of the bike on which your friend is sitting on. So let us consider that to be a different case 1 when compared to our original case. Now in this instance, we have a force, and this force we impose a force, and this force experienced by the individual atom of course is proportional to that of the positions of the atom. So let us express that by x of t. So x of t dictates the position of the atom and the F is the force that you are imposing. Now in addition to the force that you are imposing, we also find that in this case 1, your friend is also imposing a force on the same rim of the bike. So the key difference is, instead of someone stamping on an idle bike, what we are essentially observing here is, or what we are doing here is, we are kicking a bike on which your friend is sitting. So your friend is already imposing a constant force. This W is a constant force, or let's say a constant force field onto the rim of the bike, to which you are imposing an additional force, and the force that you are imposing is proportional to the positions of the atom. Now if we want to rather come up with an ODE for this, if we want to rather express what the action here in the form of an ODE, we can of course introduce a proportionality constant and write it as, let's say, kx of t, and we are multiplying a proportionality constant with respect to another constant w. So let's say it will become a w bar. So I have force, and this force experienced by the atom is equal to the position, or it depends on the position of the atoms, and also the atoms are already experiencing a constant force. So this expression now is rather an extended version of what we originally considered, and it has this additional term w bar, which speaks of the force field, the constant force field that is imposed by your friend. Now I can rewrite this expression as something like, if I assume that entire mass is, say, unit mass. So I can write this as something like the acceleration is equal to kx of t plus w, a constant term. Now what we essentially have here is I can further rewrite it as something like x of t minus k x of t, acceleration x double point minus k x of t is equal to w bar. Now what we essentially observe here is, originally when we consider this example, our w bar was missing. Originally these two were equal to 0. This was our original expression, and now we have an additional constant term which is introduced by the friend who is sitting on the bike. Now when you want to consider the form of the ODE, originally the ODE that we considered was linear and homogeneous, and what we now have is a constant that is acting, the constant that is introduced. So this is linear and non-homogeneous. So essentially we talked about differentiating different ODEs, and we said that when we have a base function, the derivative of the base function, and sum of all these when they are equal to 0, we refer to it as linear and homogeneous. Now in this case, it is not equal to 0, it is equal to a constant. So what we have is a linear and non-homogeneous ODE. So the first understanding we can gain from this discussion is that the linear non-homogeneous ODE is not something out there. It's not just a purely a mathematical consumption. We have relevance of linear non-homogeneous ODE in our physical world, meaning there are problems that we face, and the ODEs that relate to this problem, that describe this problem, can be in the form of linear and non-homogeneous equation. This is rather an example. Now you can consider this force field that your friend introduced could be, say, a magnetic field, could be an electric field. You can consider different fields, a different constant field to which the atoms are already exposed to, and you are imposing an additional force to it. Let's say, supposing your atoms are exposed to a magnetic field and you are exposing a mechanical force to it. So you place your atoms in a constant magnetic field, and you expose these atoms to a force. Then the expression will not only have the relation between the force and the position of the atom, but also the role of the constant magnetic field, and such will be the nature of the expression, and that will be our linear and non-homogeneous ODE. Now, imagine the same case 2 here. Now, instead of your friend being static and sitting on the bike, let us say your friend is bouncing on the bike, meaning the force that your friend imposes on the bike, it depends on the time. So, instead of your friend sitting on the bike, being static, let's say he is jumping on the seat of the bike. It means as the time varies, or depending on the time, the force that is imposed by your friend on the bike varies. So therefore, what critically would change in this expression is, in case 2, let's say in case 2, wherein your friend is not ideally sitting on the bike, now he is jumping on the bike. So basically what he is imposing is something called as a cyclic loading. Now in case 2, when your friend is imposing a cyclic loading, the load that is imposed by your friend is not constant, but it depends on time. So this factor here, to which your the derivative of your position relates to, is no longer a constant but a function of time, and time is the fundamental variable here, and again this leads to a linear non-homogeneous ODE. So in both these instances, in both case 1 and in case 2, what we essentially have is, we have something that is conceivable. First of all, we have something that we can directly relate to even in the simplistic example. So the key difference is the force field, the already existing force field to which the atoms are exposed to. In the case 1 it was constant, in case 2 it depends on time, it varies with time. Now the same example of the magnetic field can also be considered here. You can have a crystalline material placed in a magnetic field, and this magnetic field is varying with time. So therefore the relation between your force experienced by the atom, in addition to its position, is also can be related to that of the magnetic field. So the entire ODE that we generate in order to describe the problem that we are facing now includes this term here that depends on, it includes this term here, which depends on the fundamental variable. So therefore it ultimately leads us back to linear non-homogeneous ODE. So what we essentially then want to do is, we want to understand a technique that would help us solve linear non-homogeneous ODE. So far we have been considering linear homogeneous ODE. So what essentially we would like to do now from in this session or in the sessions to come is to understand or come up with a technique that will help us solve linear and non-homogeneous ODE. So this is rather to motivate us towards the problem which rather renders us an ODE with an additional term, with an existing forcing field that ultimately assumes a form of linear and non-homogeneous ODE. Now, if you consider this expression, let us do away with all these terms here. So, if you consider just this expression here, the acceleration, the x term that comes from the acceleration, plus that of its dependence on the positions of the atom, plus let's say the existing force field or the field that varies with time. If we consider this expression here, this expression again is a linear non-homogeneous ODE. Now, when you have this forcing term absent, when this term, that is the field term W of t, when it is absent, what we essentially have is, it is the force that ultimately governs or that ultimately dictates the change in the positions of the atoms. So we have one factor that ultimately governs the positions of the atom. So there is no other factor to restrict or regulate the position of the atom, it's just the force. So that is what we observe in the case of linear and homogeneous ODE. Now when you consider the physical significance of linear and homogeneous ODE, what it essentially states in our cases, we have a governing factor and that governing factor is the force, and the position of the atom depends exclusively on that force. So there is no other regulating factor. There is no other factor that restricts the position of the force, position of the atoms other than the force. According to the force that we impose and depending on the time, positions of the atom vary. There is no other factor that would regulate the position of the atom. But when you consider an expression such as this, which is linear and a non-homogeneous ODE, there is an additional term that essentially restricts or regulates the position of the atom in addition to the force that you impose. So basically, you have atoms that is experiencing already or placed within the force field that is experiencing already an force, and to this force you are imposing an external force. So in our case, we have a set of atoms that are experiencing already the weight of your friend, and to that you are kicking the bike, so you are imposing a force of your own. So basically now the positions of the atom is the combination of both these forces. One, the force that you impose by kicking, the other is the force that your friend imposes by just sitting on the bike. So when you extrapolate this, or when you consider this expression from this linear and homogeneous ODE, what we find is this term here, essentially it rather regulates or it modifies or it influences the position of the atoms. So originally we have linear and homogeneous ODE. In that case, the position of the atom is solely governed by the force that you impose. In the other case, in linear and non-homogeneous ODE, what this additional term does is, the way we can interpret the role of the additional term is, the additional term, it essentially regulates the position of the atom. In addition to the force that you impose, this term also influences the position of the atom. So what we essentially mean is, we have with time the change in the position of the atom. In addition to the force that you impose, this change in the position of the atom is also dependent on this additional term that is introduced, which in this case is the weight of your friend. So the entire dynamics of the evolution of the atom. So what we mean by evolution is how the position of the atom changes with time. So the entire dynamics of the problem is now being influenced by the additional term that changes our linear homogeneous ODE to that of the non-homogeneous ODE. So this term, this new term, it regulates the position of the atoms, and that is the reason why we refer to, at times we refer to this new term as the forcing term. So in this original case, when we have a linear and homogeneous system, when we don't have any other forcing term, we don't have any other force field, the atoms move solely based on the force that you impose. But when you have an additional force field that is acting, the atoms, the movement of the atoms is rather regulated by, it's forced by the already existing force field. And therefore, this term is referred to as the forcing term. So basically the key difference between linear homogeneous and linear non-homogeneous system, mathematically speaking, the sum of all these base function and its derivatives are equal to 0 in linear homogeneous. In non-linear or linear non-homogeneous, what you have is the sum is equal to some constant or a function. But when you consider it physically, In linear and homogeneous case, there is no forcing term. The movement of the atom, in our example, the movement of the atom is unrestricted. It depends solely on the force that you impose. But in case of linear and non-homogeneous, there is a forcing term that rather regulates the influence of force on the positions of the atom. So then, when we solve such an expression, we are now solving or identifying the position of the atoms which are now regulated by this additional forcing term. Now, when we solve a linear non-homogeneous ODE, what essentially we are getting out of it is still what we get out of it is x of t, that is the position of the atom. This is what we get out of it. The solution of solving a linear non-homogeneous ODE is still the position of the atom. But now, this position of the atom is not exclusively governed by the force that we impose, but also it is regulated by, or it is forced by, the force that is already the atoms are experiencing. So with this motivation, what we will do is we will try to solve the linear non-homogeneous ODE that the forcing term would generate. So this we will do in our subsequent session. Goodbye, guys.